Hello and welcome back. So now let's start off with the first test case. So this is a very simple one. This is you could think of it as a monopole in an infinite domain, but you could also think of it as a heat diffusion from a sphere in an infinite domain, or you could think of it as a spherical pellet which is diffusing solute into the media around it, right? So there are so many similar ways of looking at it. You could think of it as a sphere which is emanating an electric field or a magnetic field. So in each of these cases we are just concerned with solving del square phi is equal to 0, which means we are just considering a constant diffusion coefficient, you could say. So there is no variation. This is a purely isotropic problem, and this is situated in an infinite domain, so you could just solve it analytically. A very simple analytical solution exists, and so we will actually solve this in 3D by discretizing this domain, and so we consider a truncated domain. Of course, we cannot mesh till infinity, so we consider a truncated domain, and the effect of the far field or the effect at infinity can be captured by using a Robin boundary condition. Okay, so we'll discuss about this condition a bit later. First, let us emphasize that we want to solve this problem in 3D, and we also want to solve a 2D representation. But first, before doing that, we'll just solve a 1D case in spherical coordinates. So when you look at this cross section, this lightly shaded part is basically your sphere, and you are doing a volume integral on this sphere. So you are basically integrating this del square phi over this entire sphere's volume. You are not integrating it inside the sphere, but only outside. At the boundary of the sphere you have this Dirichlet condition, and at the outer boundary you have this Robin condition. Okay, so we are just simplifying this problem to a 1D problem over this green line here, which is just pointing radially outwards, and we are going to use spherical coordinates. So this will be a very good revision also for our 1D finite elements. And as I have already mentioned, 1D finite elements have been covered extensively in the first course, where we also solved them using spreadsheets. We did not code them, but the same analogy of the same workflow of the Excel sheet will be carried here when we actually start coding it. If you are really getting confused in any of these further slides, so you can just go back to the free course on YouTube about the 1D elements, which is the course just before this. Just the last 1 hour of that course is related to finite elements. So I'll just brush through these slides from the previous course very quickly. So let's recap a bit. So we are solving this d2u by dx square is equal to 0. This is basically just a ordinary differential equation, because we are just dealing with one dimension and there is no time discretization. So for solving this by finite elements, we multiply by a test function psi and we integrate. And in the Galerkin's formulation, we are really interested in the weak form, and this helps us because we can even use C0 functions, which are your Lagrange functions are C0 polynomials, right? C0, whether they are 2D polynomials, 3D polynomials, they are all C0, which means that the first derivatives are discontinuous. So when you use a piecewise continuous representation using Lagrange polynomials, the first derivatives are going to be discontinuous, and the second derivatives will have blow-ups at the inter-element boundaries. So you will have Dirac delta kind of functions. So you cannot really represent the d2u by dx square directly by using Lagrange polynomials. And we also discussed in the previous course that we cannot use C1 polynomials very easily. So we could use them for 1D elements or very simple problems, but we don't have any good mesh generator for 2D and 3D when it comes to C1 polynomials. So we use C0 polynomials. And this kind of a formulation really helps you to avoid breaking down the problem into two parts. So if you want to model this second derivative by C0, you can't do that. So you would have to either break it into two first order problems, or you could, if you want to solve it just like in the strong form, or you could use a weak form. So what is the weak form? So we just apply integration by parts on this psi into d2u by dx square, right? And so we get two terms here. The first term is having two first order derivatives, right? So you can see that this one derivative has transferred from the second order term to the test function. So now this is a formulation which we can handle by using C0 polynomials, and then you also have the second term which goes on the boundary, which is evaluated at the boundary, and you can see that we are getting this nice du by dx here, so we can use it to model the Neumann boundary conditions. So here you just have a pictorial representation of this 1D domain omega, and gamma is the boundary where you can apply the Dirichlet or Neumann boundary condition. So for the Neumann boundary condition, you have du by dx is equal to a, so that a can simply be plugged into this part here, right? Really we want to solve solve the problem inside this domain where this red term is applicable, and this can be done by dividing the domain, discretizing it into a finite number of elements, and these elements have piecewise continuous polynomial representations, and those representations are done by what we call as the trial functions. And to really form the integral statements, which we call as the weighted residual statements, we need weights or tests, which we also call as the test functions. So here I have shown the test functions in white and trial functions in yellow, and this is how you basically represent your integral equation. So all of this theory has been covered in the first course, and so if this is confusing, you can just go back to it. And this is just the formulation for the source, because the source is what you get on the RHS. So this becomes part of your linear form, and the left hand side, which is the diffusion term, right, which is represented by this kind of a representation with trial and test functions, right? So this is basically a bilinear form, and in case of Galerkin's, the test and the trial functions are the same. Okay, in case of Petrov-Galerkin's, they are different. In case of Galerkin's, they are the same. So in case of Galerkin's, you get a very symmetric matrix. So in case of Poisson's equation or this diffusion Laplace equation, you have symmetric positive definite matrices which are very easy to solve, right? We also looked at the mapping. So we showed how any 1D element can be simply mapped to any master element, which is so you have different types of master elements. So you could have one which is running from psi is equal to -1 to 1 or 0 to 1, or you could define any master element of your own, but those two are the most commonly used. And then you have these Lagrange polynomials defined on the master elements, so like 1 minus psi and psi, and this mapping of x as well as u, so both the unknowns as well as the knowns can be mapped to this master element through this mapping, which is basically called as isoparametric mapping, because we are using the same kind of mapping for both the unknowns and the knowns, but we could also use different mappings. But in this course as well as in the previous one, we just used isoparametric mappings, and that is the most commonly used method. And then we also looked at how we derive these derivatives of the shape functions or the polynomials. So we apply the chain rule, and we just multiply it with the derivatives of our master element, right? So that is how we do the transformation between the master element and the physical element. And then we do the integration by using Gaussian quadratures, so we had covered that as well. So really this gives us this kind of a local stiffness matrix, a local force vector. The RHS is called as a force vector or load vector, and then you have this unknowns vector, right? And then you just assemble all of the elements together, and this gives you a global stiffness matrix. You apply the boundary conditions on that global stiffness matrix, and then you invert it and solve. You apply the boundary conditions, of course, on both sides, and not just on the stiffness matrix and the force vector as well. And then after inversion, you can just get your unknowns vector. So we saw all of this in the previous course, and now let's apply this to our test problem. So our test problem is the